My point of discussion is to find a relation between magnetic field as well as electric field. The first simple experiment done by Oersted, which was just a very simple experiment. It was called Oersted experiment. In this experiment, one magnetic needle was placed just below the conductor. When current passes through the conductor, the needle gets deflected. So, see, this is very interesting. So, without passing, some magnetic effect is produced, because we know that North Pole repels North Pole. So, how it is deflected? There might be some magnetic field around the conductor. So, it was the experiment, very simple experiment. But Oersted, unable to deduce, unable to calculate the exact magnetic field around the conductor. So he just demonstrated the effect. So from this experiment, it was clear that there is a close relation between magnetic field and electric field, because needles are deflected. Okay, needles are deflected. That is why some magnetic field is produced here. So when current passes through the conductor, it might produce some magnetic field, which in turn affect this needle. Okay, the experiment is very small, but its effect, its discussion was a great contribution for the scientist. Okay, it gives clear evidence that there is a close relation between magnetic field as well as electric field. But Oersted unable to calculate the exact value of magnetic field around this conductor. Next, two people came. They able to find the magnetic field around any conductor at any particular point. That scientists were Biot Savart. Okay, Biot Savart. According to their name, the law is called Biot Savart law, right? So let us discuss what is Biot Savart's law. So if we consider a current carrying conductor, this is a current carrying conductor. It carries a current I. Okay, it has some length, and Biot and Savart calculated magnetic field at a particular point P, suppose. So in their experiment, they found the effect produced by this current carrying conductor, the magnetic field produced at point P. Okay. So let us consider an elementary length, okay, dl, and O be the center of the elementary length. Dl is the length of the conductor, and position vector of the point P from the O is R, and it makes an angle theta, suppose orientation. Theta is the orientation, and dl is the length, I is the current, R is the distance. Then the magnetic field, small amount of magnetic field produced by this elementary length at point P, the magnitude is given by dB, which is directly proportional to the current. What does it mean? It means that the intensity or the strength of magnetic field at point P produced by this current carrying conductor is directly proportional to the flow of current. When you increase the current, the magnetic field induction will also increase. When you decrease the amount of current, the value of magnetic field also decreases. This is first factor. Another factor is dl. dl, the value of magnetic current element. The value of current element, that is, if you expose this current element to this particular point, if you increase the value of dl, the effect will also increase. That is, the magnetic field induction will also increase when you increase dl. That is, dB is directly proportional to dl. Okay. Third factor is theta. Theta cannot stand alone. That is why it is sine theta. Because when theta increases, sine theta also increases. That is why instead of taking theta, they have taken sine theta. Okay. Where theta is the orientation of this conductor, or with respect to the point P, or you can say that the point P has some orientation theta at this central point, right? Now, the last factor is the square of the distance. It is the value of position vector from the center of the current element up to point P. This is the experimental point. So it is inversely proportional. When you take away, when P is taken away from this conductor, then this value will decrease. When you come closer, then this value will increase. So it is inversely proportional, right? Now, if you combine them together, according to mathematics, you will be in need of one constant. That constant is mu naught by 4 pi. Okay. Then I dl sine theta by r square. Okay. Equation 1. This is the scalar form of Biot Savart law. Okay, this is the scalar form. Okay, that is this equation gives the magnitude of magnetic field produced at point P. But magnetic field is the strength of magnetic field, or the magnetic field induction is a vector quantity. It might have some direction. Okay, so this gives only the magnitude. So it should have some particular direction. So that is, there may be some vector form also. This is scalar form. So let us find the vector form. Okay. Now, equation 1 implies, this is equation. So let us multiply both numerator and denominator by I dl r. Okay, multiplying both numerator and denominator by r. So r is multiplied, it will be r cube, right? Now we can write, if we write dB as a vector quantity, okay, then right hand side should also be a vector quantity. So we can combine these quantities together to give a cross product. How? See, dl cross r vector. If you write dl as a vector, r is a vector, then you can write dl cross r. Okay, then r cube. So this is equation number 2. Equation 2 is called vector form of Biot Savart law, right? This is the Biot Savart law, and this is second equation. That is, we are writing dB in a vector form, and we are writing dl r sin theta as vector form, right? So why we are writing dl r sin theta as dl cross r? Why? As you know that if we write a cross b This is cross product. As you have got in class 11. This is cross product. And if you want to write it, then AB sine theta n cap. What is theta? Theta is the angle between A and B. Okay. So if you consider that DL has some direction along the direction of current, so DL will be a vector. So R vector, it is a position vector. Theta is the angle between them, right? So DL can be written as a vector because it has a direction along the direction of current. B, in place of B, the R vector, R has a direction this. So angle between them is theta. So it can be replaced as AB, not AB, it is DL R sine theta or n cap. Sine theta into n cap. So n cap is the unit vector. So in this way, we can convert scalar form into vector form. So another important point, what is the direction of dV? Okay, this equation gives the magnitude of magnetic field and this equation gives the direction of magnetic field. So let us see what is the direction of magnetic field. As you know, when we write A cross B, okay, when we write A cross B, it is represented as C, suppose. A cross B is equal to C. So it gives, if you imagine the screw rule, if you go from A to B, C will be along upward direction. Suppose A cross, you are going from A to B, A cross B. So A cross B in a plane and C is perpendicular to A cross B, right? So if A cross B is equal to C, it means that C is perpendicular to both A and B. In the same way, dV vector is perpendicular to both DL vector and R vector. Okay. So from that we can write that dV vector, which is the magnetic field at this point P, must be perpendicular to both DL and R. So here you will find dV in such a way that dV should be perpendicular. dV should be perpendicular to both R vector as well as this vector. Okay, on this conductor. So this is the method how to find out the magnitude of magnetic field as well as the direction of magnetic field. This gives the direction which is perpendicular to both R and DL vector. Okay, R vector and DL vector. So this is very important. Okay, by using this you can find out the magnetic field around a circular conductor, at a center of circular conductor when current flows through the conductor, or in some solenoid, suppose magnetic field on the axis, or due to a straight conductor, infinitely long straight conductor, you can find out the magnetic field produced. Okay, so this is all about Biot Savart's law. This is very important.